Okay, let's talk about Hadoop. Essentially, it's a really powerful tool for dealing with huge amounts of data. We're talking terabytes or even petabytes. Imagine trying to analyze all that information on a single computer. It would take forever. Hadoop solves this by splitting the data into smaller pieces and distributing them across many computers working together in a cluster. It's built around three main parts: HDFS, which is like its storage system, making sure copies of your data are safe and reliable; MapReduce, which is how the processing happens, breaking down tasks and running them simultaneously; and Yarn, which manages all those resources across the cluster to ensure everything runs smoothly. The biggest reason to use Hadoop is that it can scale with you as your data grows. It's very resilient to failures, and it's generally a much cheaper option than traditional database systems for handling massive datasets. Okay, let's talk about the core pieces of the Hadoop ecosystem. First up is HDFS. It's like a super distributed hard drive that spreads your data across many computers in your cluster to make sure nothing gets lost and everything is always available. Then we have MapReduce, which is how you actually do something with all that data. It's a way of breaking down big problems into smaller pieces that can be tackled by multiple machines working together. Next, Yarn manages the resources within your cluster. It decides who gets to use what and when. Hive lets you talk to Hadoop using SQL if you're used to databases, making it easier for everyone to work with the data. HBase is a NoSQL database that's really good at handling fast reads and writes, while Spark has a newer engine that can process data much faster than MapReduce. In certain situations it uses memory instead of relying on disk storage as much. Okay, let's talk about HDFS. It's really the backbone of Hadoop. Basically, it's a super scalable storage system that breaks your massive data into smaller blocks and spreads those blocks across many computers in your cluster. This makes things incredibly reliable. If one machine goes down, you don't lose your data because there are copies stored elsewhere. It also means you can easily add more machines to handle even bigger datasets as they grow. HDFS is all about distributing the load and ensuring that your data is always accessible. Okay, let's talk about the name node. It's a really important piece of the Hadoop puzzle. Basically, it acts like a super organized librarian for your files. Instead of keeping copies of all your data itself, the name node keeps track of where everything is stored in the cluster. It knows exactly which data nodes hold each block of data and how to find it quickly. It's essentially a master directory holding all the metadata, things like file names, sizes, permissions, and most importantly, where those files are physically located across all the data nodes. Okay, let's talk about data nodes. They're really the workhorses of HDFS, where your actual data lives. A data node is essentially a server that holds chunks or blocks of files. It spreads these blocks out across multiple servers to make sure if one server goes down, you don't lose any information. It's all about redundancy and reliability. The system keeps copies of everything so you always have access. Okay, let's talk about the secondary name node. It's a really important piece of the Hadoop puzzle. Basically, it's like having a reliable backup and a super fast assistant for your primary name node. It constantly keeps copies of some metadata, so if the main name node goes down, you don't lose everything. It also caches frequently used data information, which speeds things up considerably when clients are requesting file details. And it helps with managing how data is replicated across all those data nodes to make sure your files are safe and available. Okay, let's talk about HDFS. Think of it as a really robust way to store massive amounts of data across a bunch of computers. The core idea is that we break down files into smaller pieces called blocks. These blocks are then spread out and copied onto multiple servers. These are the data nodes. The name node acts like a directory manager, keeping track of where all these blocks are located. It's important to remember it doesn't actually store the data. That's the job of the data nodes. And because HDFS keeps copies of each block in different places, if one server goes down, you still have access to your files. That's what makes it so reliable. It's particularly well suited for tasks where you need to process huge amounts of data at once. Okay, let's talk about blocks in HDFS. Imagine you building something big with Lego bricks. That's essentially what blocks are in Hadoop. Each file you store isn't just one giant piece of data, it's broken down into 128 megabyte chunks called blocks. These blocks are then copied and stored on multiple machines, or data nodes, to make sure your data is safe and available even if some machines go offline. It's a really important concept for understanding how HDFS works. Okay, let's talk about how Hadoop handles failures. It's a really important aspect of its design. Basically, Hadoop is built to keep running even if things go wrong, and they will. The key thing it does is data replication. Think of it like making multiple copies of your files and spreading them across different computers in the cluster. If one computer fails, you still have those copies available. It also has a backup name node that kicks in if the main one goes down, ensuring you can always see your file system. And the MapReduce tasks are split up, so if one worker breaks, another takes over. Plus, it regularly saves its progress to make recovery super fast. Okay, let's talk about data replication in Hadoop. It's all about making sure your data doesn't disappear if one part of the system goes down. Think of it like having multiple copies of an important document stored in different places. If one copy gets damaged or lost, you still have backups. Hadoop uses a replication factor, usually set to 3, which means each piece of data is copied onto 3 different machines within the cluster. This makes the entire system incredibly reliable and fast. Okay, let's talk about how HDFS keeps track of everything. It's actually managed by something called the name node. Think of it as a central directory or librarian for your files. The name node doesn't store the actual data itself that lives on the data nodes. Instead, it holds all the information about the files, where they are stored, how many copies exist for redundancy, and other important details like permissions. It does this using something called metadata blocks. And because HDFS wants to be super reliable, these metadata blocks aren't just kept in one place. They're replicated across multiple data nodes to make sure nothing gets lost if a node goes down. So basically, the name node is responsible for keeping all that information organized and accessible. Okay, let's talk about what happens if our Hadoop name node goes down, a critical scenario. Thankfully, HDFS is built with redundancy in mind. We have secondary name nodes that act as backups and replicate the metadata. If the main name node fails, one of these secondaries steps up to take over. It's like a backup system. And because data is replicated across multiple data nodes, usually 3 copies, losing a single data node doesn't affect the availability of your files. The client will automatically connect with the new primary name node, so it just continues running as usual. Okay, let's talk about rack awareness, a really important concept when we're thinking about Hadoop clusters. Basically, it's all about figuring out where to put your data so that things run smoothly and quickly. Imagine you have a bunch of servers spread across different racks in a data center. A rack is like one room in the building. A rack awareness algorithm helps us decide where to store data blocks. Think of them as individual files to minimize how far the data has to travel, which significantly reduces network latency. Why does this matter? Because if your data is close to where it's being processed, everything runs much faster. We use things like consistent hashing and erasure coding to make sure we can handle failures gracefully too. Okay, so how does data actually make its way into HDFS? It's not a single operation. Think of it like this: we chop your big file up into smaller pieces called blocks, usually around 128 megabytes each. Then, for safety and reliability, we create multiple copies of each block and spread them across different computers in the Hadoop cluster. The name node is like the librarian, keeping track of exactly where all those copies are stored. And to make sure nothing gets lost, there's a log that records every change before it happens. It's a clever system designed to handle massive amounts of data and keep everything running smoothly. Okay, let's talk about how Hadoop actually gets the data it needs from its storage system HDFS. Imagine you have a huge file spread across many computers in your cluster. HDFS isn't just dumping everything into one place, it breaks it down into smaller blocks, usually around 128 or 256 megabytes each. When an application wants to read that file, it doesn't ask for the whole thing at once. It first talks to the name node, kind of like a librarian in this case. The name node figures out exactly which computers have which blocks and then tells your application precisely where to go to grab them directly. It's all about distributing the work and making sure everything happens efficiently, so you can quickly read through those massive data sets. Okay, let's talk about Hadoop 1x versus 2x, a really important shift in how we think about big data. In Hadoop 1x, everything ran within a single cluster, and any failure could bring the whole system down. It relied almost exclusively on MapReduce for processing. Then came Hadoop 2x, which introduced Yarn. Think of Yarn as a traffic controller for your cluster. It manages resources dynamically so you can run different applications simultaneously, and it's much more resilient to failures. Essentially, 2x is all about scalability, flexibility, and making Hadoop even easier to work with. Okay, let's talk about Yarn. It's a really important piece of the modern Hadoop ecosystem. Think of it as the brain behind how your Hadoop cluster uses its resources effectively. Before Yarn, the MapReduce framework did everything scheduling jobs and managing all the computer power. That was clunky. Yarn changed things by separating those two responsibilities. It's divided into a resource manager and node managers, working together to make sure everyone gets what they need. Basically, it lets different applications like traditional MapReduce, but also newer ones like Spark or Hive share the cluster's resources smoothly, making Hadoop much more versatile and powerful. Okay, let's talk about Yarn. It's a really important part of Hadoop because it separates the job processing from the data storage. Think of Yarn as having three main players: the resource manager, which is like the brain of the operation, coordinating everything and deciding where jobs should go. Node managers, these are the actual worker nodes in your cluster. They do the heavy lifting. And then there's the application master, which is responsible for managing a specific application's tasks and ensuring everything runs smoothly. It's a clever way of handling different types of workloads within Hadoop. Okay, let's talk about the resource manager in Hadoop. It's honestly like the brain of the whole system. Its primary job is to keep everything running smoothly. It manages all those individual worker nodes, called data nodes. The resource manager decides where each piece of work needs to go and makes sure that things don't get stuck if a node goes down. It's constantly watching the cluster for any problems and then automatically figures out how to pick up the slack. Okay, let's talk about the node manager in Hadoop. It's essentially the brain of each individual worker node in your cluster. Its primary job is to keep track of exactly what resources like CPU and memory are available on that node. Then it uses this information to decide where to send tasks from MapReduce jobs. If a process crashes, the node manager steps in and restarts it automatically. It's constantly monitoring everything and making sure things run smoothly. A healthy node manager is key to a well-performing Hadoop cluster. Okay, let's talk about application masters in Yarn. They're crucial for managing applications on the cluster. Think of them as the main hub for a MapReduce job or any other long-running process. The application master is responsible for scheduling tasks, making sure they have enough resources, constantly monitoring their progress, and even handling failures if something goes wrong. It's like the conductor of an orchestra. It keeps everything in sync. Okay, let's talk about the heart of Hadoop MapReduce. Imagine you have a huge database that's too big for one computer to handle. That's where MapReduce comes in. It's essentially a clever way to split up a really big job into smaller, manageable pieces and then get lots of computers to work on those pieces at the same time. The map phase is like reading all the data and turning it into pairs. Think of keys and values. Then the reduce phase takes those pairs, groups them by key, and does some final processing to give you your answer or result. It's a fundamental concept, so understanding this duality is really important for any Hadoop interview. Okay, let's talk about the different stages involved in a Hadoop MapReduce job. First, we need to read our data from HDFS. It's broken down into smaller pieces. Then comes the map phase where your mapper function does its thing, turning each piece of data into key-value pairs. Next up is shuffle and sort, which groups all the values associated with the same key together. Finally, we hit the reduce phase, where the reducer combines these group values to give us our final result, and it's written back to HDFS. Okay, let's talk about the mapper. It's one of the core components in Hadoop's MapReduce framework. Basically, the mapper is like a first line of defense for your data. It takes massive amounts of input, think huge files or streams, and breaks it down into smaller pieces. The mapper uses a specific function, that **right, to transform each piece of data into a key value pair. So, you're defining how the data should be categorized and counted. It's all about taking raw information and preparing it for the next data reducer. Okay, let's talk about the reducer phase in Hadoop. After the map stage, we have a massive collection of key value pairs. The reducer's job is to take all those pairs for each unique key and do some serious work on them. Think of it like this: the mapper broke down the data into smaller pieces, and the reducer puts those pieces back together, often by aggregating or transforming the values associated with each key. It's a crucial step for combining and condensing the information before writing it to disk. Okay, let's talk about combiners. In MapReduce, we want to make things super efficient. Imagine each map task is churning out a massive pile of intermediate key value pairs. If these piles are huge when they reach the reducers, that's going to slow everything down. That's where combiners come in. They're like mini reduce operations that happen inside each map task. Essentially, they take all the values associated with the same key and combine them into a smaller set before sending it off to the reducer. This dramatically cuts down on the amount of data being transferred, leading to much faster processing times. Think of it as pre-reducing the data within each map job, making the reducer's lives easier. Okay, let's talk about the partitioner in MapReduce. Think of it like a sorting clerk who decides which reducer gets each piece of data based on its key. The partitioner takes the key that's the identifier for your data and spits out an integer. That integer is essentially the ID number of the reducer that should handle that specific piece of data. The default, or most common, method is using a hash function to figure out which reducer gets what. It's really important because if you don't have a good partitioner, some reducers might get overloaded while others sit idle, and that slows down the whole process. Okay, let's talk about how MapReduce gets its data. The first thing you need to know is that it needs something to work with, and that's the input format. Most commonly, we deal with text files, think logs or documents, where each line represents a record. Then there's Hadoop's own sequence files, which are great for large binary datasets. Avro and Parquet are more advanced formats. Avro is good for managing schemas over time, and Parquet is super efficient for analytical queries due to how it stores data column by column. Finally, you might encounter JSON or CSV files, but generally those aren't the most optimal choices for MapReduce performance. Okay, let's talk about how MapReduce organizes its results. Initially, each map task produces key value pairs. That's the basic unit of information. These pairs are then sorted based on the keys and written to HDFS as text files. The specific format these files use varies depending on what you configure. You have options like text file format, which is straightforward but can be less efficient for complex data. Sequence file format offers a more compact binary storage method, great for nested data. Avro output format excels at integration with other systems due to its schema-based approach. And finally, object file output format stores each key value pair as a separate object in HDFS, often combined with compression like Snappy or LZO to save space and speed up retrieval. Okay, so after you've done your mapping, which breaks down the big problem into smaller pieces, you end up with a ton of intermediate results. These are all jumbled together. The shuffle and sort phase is where MapReduce really starts to shine. It's essentially like sorting a giant pile of papers by topic. Each mapper sends its output to the correct reducer based on the key. And once the reducer gets all the data for a specific key, it sorts that data usually in order of the key itself, making it super easy for the reducer to process everything efficiently and produce the final result. Okay, let's talk about speculative execution in Hadoop. Think of it as Hadoop's way of anticipating what a mapper might do before it actually finishes. It's like a little shortcut. Basically, when a map task is taking too long, Hadoop figures out what asterisk that map might be producing and starts running copies of the mapper code in parallel. These are called speculative mappers. If one of those speculative mappers completes successfully with correct results, Hadoop uses it directly, skipping the need for the original mapper to finish. It's all about speeding things up, but there's a little extra work involved in managing these copies and making sure they don't introduce errors. Okay, let's talk about two key players in Hadoop: the job tracker and the task tracker. The job tracker is like the conductor of an orchestra. It's a central server that manages all the jobs running in your cluster. It figures out how to break down those jobs and assigns them to the right people, which are the task trackers. Task trackers, on the other hand, are the actual workers. They're the nodes where the data processing happens. They receive instructions from the job tracker about what tasks to perform and then do the work themselves, reporting back their progress along the way. Okay, let's talk about why Yarn was such a big deal in Hadoop 2x. Before this, Hadoop 1x had a really tight coupling between managing all the cluster's resources and actually running the jobs themselves. It was like one central controller doing everything. But as clusters got bigger, that single control of the resource manager became a major bottleneck. It also struggled to handle different types of workloads. It wasn't designed for things besides simple batch processing. Yarn changed all of that. It separated out resource management from job scheduling. Now you have a resource manager focusing on allocating resources and node managers handling the actual task execution. Each application gets its own manager, which makes the whole system much more flexible and scalable. Okay, let's talk about submitting a MapReduce job. It's an important step for getting your data processed. You'll generally use the Hadoop jobs command with some options. But before you do that, you need to create a job configuration file, which basically tells Hadoop everything it needs to know: where the input is located, where the output should go, and what kind of processing to do. You'll specify the paths for both the input data in HDFS and the desired location for the results. Then, you define how many mappers and reducers you want to use. It's a good idea to double-check your configuration file carefully before submitting. Any mistakes that can cause problems. Let's talk about counters in MapReduce. Think of them as super simple, but incredibly important ways to keep track of things during your jobs. Basically, they're just counting machines. Each map and reduce job starts with a counter set to 0. When the mapper finds a new key, it increases that counter by 1. And when the reducer gets all the counters for a specific key, it adds them up to get the total count. Without these counters, combining results from multiple mappers would be a real headache. Counters make the whole process much smoother and more reliable. Okay, let's talk about sequence files. Think of them as a super organized way to store data within Hadoop. Basically, they're just collections of key-value pairs like a giant spreadsheet. But unlike simple text files, these are serialized, meaning Hadoop converts Java objects into bytes so it can efficiently store and process the information. They also often come compressed, which saves space and makes transfers faster. And here's the clever part. A sequence file keeps track of where each piece of data is located using a metadata file, so when you need specific information, Hadoop only reads what it needs, no unnecessary digging. They're particularly useful when dealing with large datasets because they're much more efficient than just plain text files. Okay, let's talk about the distributed cache in Hadoop. It's a super handy tool when you're dealing with data that's too big to fit comfortably inside the memory of a single mapper or reducer. Imagine it as a shared workspace for all your tasks, mappers and reducers alike. When a map task needs some information, instead of constantly going back to HDFS, it can quickly grab it from this cache. It's automatically cleaned up when a task finishes, so you don't have to worry about memory issues. You'll often see it used for things like configuration files or small datasets that are needed by multiple tasks during processing. Really helpful for debugging and testing too. Okay, let's talk about Hadoop streaming. It's a really clever technique that simplifies how we work with massive amounts of data using the MapReduce framework. Think of it as a way to tell Hadoop what to do without needing to write complex Java code. You essentially break down your processing into two steps: mapping and reducing. The mapper reads from a text file, transforms each line, and writes key value pairs to another file. Then the reducer takes all those pairs, groups them by key, and applies some logic like summing up values or counting occurrences to give you the final result. It's a super flexible way to handle data processing. Okay, let's talk about how HDFS compares to your everyday file system. Think of a regular local file system. It lives on one computer and can only handle so much data. Its scalability is limited by that single machine's capabilities. Now HDFS is completely different. It spreads the data across many computers in a cluster, making it incredibly scalable. You can throw massive amounts of information at it. Crucially, HDFS replicates your data across multiple machines, so if one machine fails, your data isn't lost. That built-in fault tolerance is a huge benefit for reliable big data processing. Okay, let's talk about how Hadoop deals with a situation that can be tricky: lots of tiny files. Initially, traditional file systems just weren't built to handle this well, which could cause problems for performance. But Hadoop has some clever tricks up its sleeve. It uses something called MapReduce, which breaks down big jobs into smaller pieces that can be processed independently. It also employs input formats and record readers to read these files efficiently. The core idea is splitting those small files into smaller splits-like chunks and then distributing them across the cluster so they can be processed at the same time. And if you need a final combined result, there is a merge phase that brings everything together. Basically, Hadoop's design lets it handle multiple small files really effectively by spreading out the work. Okay, let's talk about Hadoop clusters. Imagine you have a huge amount of data way too big for one computer to handle. That's where a Hadoop cluster comes in. It's like building a team of computers working together as one giant unit. Each computer, or node, stores a piece of the data using HDFS, which makes sure nothing is lost if one machine fails. Then, MapReduce takes that data and breaks it down into smaller parts to be processed at the same time on all those computers. It's like having hundreds of workers tackling a single project simultaneously. Okay, let's talk about daemons in Hadoop. Basically, a daemon is like a background process that just keeps running quietly in the background, doing its job without you having to tell it what to do directly. They are super important because they handle things like storing your data and making sure everything runs smoothly behind the scenes. You've got names like name node, data nodes, and resource manager, each with a specific role, but all of them are daemons working together to make Hadoop work. Okay, let's talk about managing the core Hadoop services. It's a really important part of understanding how the system works. Hadoop isn't just one piece, it's actually a cluster of different components, like the name node, which keeps track of all your files, and the data nodes where those files are stored. Then there's the resource manager and node managers. These handle resources across the whole cluster, and for newer versions, we mostly use Yarn to do that. Knowing how to start and stop these services is crucial. When starting, you'll typically use commands like start yarn sh for the resource manager and start yarn node sh on each individual node to get those node managers running. Stopping them follows a similar pattern: stop yarn sh for the resource manager and stop yarn node sh again on each node. It's a pretty straightforward process once you understand which command is responsible for each component. Okay, let's talk about the secondary name node. It's often overlooked but seriously important in HDFS. Imagine the primary name node as the main boss managing all the files and their locations. The secondary name node is like a super reliable backup operator and a quick access point for frequently used data. It keeps copies of those blocks, caching them locally, so if the main guy goes down, this backup can step in and keep things running smoothly. Plus, it backs up the primary's metadata, providing an extra layer of protection. It's all about speed and reliability. Okay, let's talk about checkpoints in Hadoop. Basically, a checkpoint is like a snapshot of a data node. It grabs a picture of everything the node is working on at a particular moment. This is super important because if one of those data nodes goes down, Hadoop doesn't have to start building that data from scratch again. Instead, it can quickly restore its state using the most recent checkpoint, which saves a ton of time and effort. It's all about making Hadoop really robust against failures. Okay, let's talk about data compression in Hadoop. Basically, when you're dealing with massive amounts of data spread across a cluster, storage costs and network transfer can become huge problems. Compression is key to solving this. Hadoop itself has built-in support for compressing the data as it moves around both before processing and after. It uses algorithms like gzip and LZO, and you can even configure which one Hadoop should use by tweaking its configuration files. And tools like Hive and Pig work seamlessly with this compression too. It's a really important aspect of managing large datasets efficiently. Okay, let's talk about compression in Hadoop. It's a really important part of how Hadoop handles huge amounts of data. Basically, Hadoop uses different codecs. Think of them like fancy ways to squeeze the data to make it smaller and faster to move around. The most popular one is gzip, which balances speed and compression pretty well. Snappy from Google is super fast but uses less CPU power, so it's great for when you need things moving quickly. LZO was once really common, but it has some licensing issues now. Bzip packs data incredibly tightly, though it takes longer, and it's ideal if you just want to save a lot of space. And finally, Deflate is the algorithm behind gzip and Snappy. It's reliable and generally fast too. The best codec depends on what you're doing. Are you prioritizing speed or saving as much space as possible? Okay, let's dive into Zookeeper. It's a really important piece of the Hadoop puzzle. Basically, Zookeeper acts like a central control panel for all the different parts of Hadoop. It helps each component find what it needs, keeps track of settings, and makes sure everything is running smoothly without any conflicts. It's particularly useful for things like finding the main server in Hadoop, managing changes to configuration files, and ensuring that only one main server is active at a time. Think of it as the glue that holds the whole system together. Without it, Hadoop would be much harder to manage and less reliable. Okay, let's talk about Apache Hive. Think of it as a way to make working with massive amounts of data in Hadoop much easier for people who are already familiar with SQL. It's essentially a database system built on top of Hadoop. Instead of having to write complicated Java code to access and analyze your data stored in HDFS, you can use standard SQL-like queries HiveQL really to get the insights you need. It translates those SQL requests into jobs that run across the Hadoop cluster. And because it's based on Hadoop, it plays really well with all the other tools in the ecosystem like HDFS and Spark. Okay, let's talk about Apache Pig. It's a really useful tool when you're dealing with data that isn't neatly organized like in a traditional database. Imagine you have log files, sensor readings, or social media feeds, all kinds of messy data. Pig is designed to make it much easier to process these types of data sets. It's essentially a language called Pig Latin, and you write instructions describing what transformations you want to apply to your data, like filtering, sorting, joining, and grouping. Pig then translates those instructions into MapReduce jobs that run on the Hadoop cluster. It's all about making big data processing more approachable. Let's talk about HBase. It's a really cool database that lives within the Hadoop world. Basically, it's like a SQL database, like MySQL or PostgreSQL, but designed to handle massive amounts of data. Instead of having a super strict blueprint for how your data is organized, HBase is much more flexible. It uses column families, which are essentially groups of related data. This means you can add new columns without messing up the whole structure. It's also built for speed. It's designed to give you really fast access to information when you need it. And because it runs on Hadoop, it plays nicely with all the other tools in the ecosystem. Okay, let's talk about Flume. It's like the delivery service for your big data. Basically, Hadoop is great at storing and processing structured data, but it can get a bit overwhelmed when you're dealing with tons of logs or streams. That's where Flume comes in. It gathers all that raw data, things like website activity, server logs, anything streamy, and funnels it into Hadoop for analysis. It has different parts. Source agents pick up the data from wherever it's coming from. Channels act as a temporary halting area to make sure everything gets delivered smoothly. And sync agents actually put the data where you want it, like HDFS or Hive. Okay, let's talk about Hadoop. It's a really handy tool in the Hadoop world. Basically, it acts as a connector between your traditional relational databases like MySQL or Oracle and Hadoop. It takes data asterisk from asterisk those databases and loads it asterisk into asterisk Hadoop, making it available for processing. And conversely, it can also move data asterisk out of asterisk Hadoop back into your databases. It handles all the tricky details behind the scenes, so you don't have to worry about how to best structure or transfer the information. Okay, let's talk about Whozy. It's not a piece of Hadoop itself, it's actually a workflow scheduler. Imagine you have a really complicated data analysis that needs to run several different steps, maybe some MapReduce jobs, some Hive queries, and even Spark tasks all chained together. Whozy is what makes sure asterisk everything asterisk runs in the right order. It takes a description of these steps, often written in an XML file, and uses it to schedule them on your Hadoop cluster, managing dependencies and retrying failed tasks so you don't have to worry about things falling through the cracks. Okay, let's talk about how Hive differs from HBase. Both are part of the Hadoop ecosystem, but they're built for very different things. Hive acts like a SQL interface on top of Hadoop. You can write queries that look familiar if you know SQL, and it translates them into jobs to process data stored in HDFS. Think of it as bringing database-like querying to your big data. HBase, on the other hand, is a NoSQL column family store. It's designed for really fast access to individual pieces of information, like reading or writing a specific row at any time. It's great for operational workloads where you need quick responses. So Hive focuses on asterisk what asterisk you want to do with your data, while HBase is all about asterisk how asterisk you store and quickly get to it. Okay, let's talk about how data is structured when we're talking about Hadoop. We have two main categories, structured and semi-structured. Structured data is like a really neat spreadsheet. Everything has its place, it's predictable, and you can easily ask specific questions of it. Think customer information or sales records. Now, semi-structured data doesn't fit neatly into rows and columns like that. It might have some organization like labels or tags, but the format is a bit more flexible, more variable. You'll find this in things like JSON files, log files from web servers, or even social media posts where the structure changes all the time. Let's talk about Pig Latin in Apache Hadoop. It's a fantastic tool for working with large datasets. Basically, it simplifies the process of moving and transforming data. We call that ETL. Think of it like this. You load your data into Pig using a load statement, then you chain together transformations like filtering, grouping, joining, sorting, and even applying custom logic. The really cool part is that Pig handles all the complicated details behind the scenes. It uses a virtual data flow engine to translate your code into MapReduce jobs, so you don't need to be an expert in Hadoop itself. Okay, let's talk about the Hive metastore. It's a really important piece of the puzzle when working with Hive in Hadoop. Basically, it's like a central database that keeps track of everything related to your Hive tables, how they're structured, where their data is stored, and who has access to them. Without this, querying data would be incredibly slow because Hive would have to search through the entire HDFS file system every time you wanted to run a query. It's all about efficiency. Okay, let's talk about Hive partitions and buckets. Imagine your Hive table as a really big filing cabinet. Partitions are like folders. In that cabinet, they help you quickly locate specific sections of information when you need them. Think of it as filtering by date or region. Then, within those folders, we have buckets. Buckets are smaller containers inside each partition, allowing Hive to distribute the data evenly and efficiently across those folders. Essentially, partitions tell Hive asterisk where asterisk the data is located, while buckets dictate asterisk how asterisk the data is organized within those locations. It's all about optimizing query performance by reducing the amount of data that needs to be scanned. Okay, let's talk about how a scoop gets your data from a traditional database like MySQL or PostgreSQL into the big world of Hadoop. Basically, a scoop is your friendly data translator. It first connects to your RDBMS using details you provide, think username, password, and database address. Then it picks out the specific tables you want to move. You can tell a scoop how to do this: either just copy everything over, create new tables in Hadoop that mirror the source, or load data into existing ones. It also has options for mapping column names if things aren't perfectly aligned between your database and Hadoop. Finally, it knows exactly where in Hadoop you want to put all of that imported information, usually a Hive table or a specific directory within HDFS. It's really like building a bridge between the familiar structure of an RDBMS and the flexibility of Hadoop. Let's talk about how Flume actually grabs those log files and gets them into Hadoop. Basically, Flume acts as a pipeline. It starts with source agents that sit near the applications generating the logs, like your web servers or apps. These agents listen for new log files being created. Then Flume uses channels to buffer the data temporarily, which is really handy if there's a sudden surge in logging. This buffering helps prevent data loss and handles things smoothly. Finally, the buffered data flows to sync agents, which are responsible for delivering those logs to their final destination, often HDFS or other storage systems within your Hadoop cluster. Okay, let's talk about input splits in Hadoop. Think of them as chunks of your data that a single mapper gets to work on. Each map task is assigned just one of these splits. It's like giving someone a specific chapter from a book to read. Splits are usually around 128 MB to 256 MB, but you can adjust the size. Hadoop tries really hard to make sure that each mapper gets data stored close by, which helps speed things up because less data needs to travel across the network. Understanding splits is key to understanding how MapReduce works and optimizing your jobs. Okay, let's talk about record readers in Hadoop. Basically, they're the bridge between your raw data and the map tasks that do all the heavy lifting. Imagine you have a huge CSV file. A record reader takes each row of that file, breaks it down, figures out what the key and value should be for the map task to understand it, and then packages everything up in a way that can be sent over the network efficiently. There are different record readers designed for different data formats, like CSV or AVRA, so you'll choose the right one based on your input. Okay, let's talk about securing your Hadoop cluster. It's not a set it and forget it thing. First off, we need to make sure people asterisk who they claim to be, so Kerberos is essential for strong authentication. Then, we need to control what those authenticated users can actually do with the data. Ranger or access control lists are your best friends here for authorization. Don't forget about encrypting your data at rest, both in HDFS and during network transfers. And finally, constantly monitor your logs. Auditing is crucial to catch any unusual activity. Think of security as a continuous process, not a one-time fix. Okay, let's talk about Kerberos. It's a really important part of Hadoop security because it helps ensure only authorized users and applications can access resources. Basically, instead of sending your password around, which is risky, Kerberos uses something called tickets. Think of it like a digital pass that proves who you are. The KDC, that's the Key Distribution Center, is the central authority that issues these tickets based on a user's identity and then verifies them when they try to access other services in the Hadoop cluster. It all revolves around principals, which are unique identifiers for users or applications, and service principal names, which identify the specific service you're trying to reach. Kerberos provides a much more secure way to authenticate compared to traditional password-based methods. Okay, let's talk about the big difference between how we traditionally store data and how Hadoop approaches it. Think of a regular database like a well-organized filing cabinet. Everything has its place, and you know exactly where to find it. It's great for things that need to be super reliable and consistent, like banking transactions. However, when dealing with massive asterisk amounts of data, think millions or billions of log files or social media posts, traditional databases can struggle. Hadoop is designed differently. It's like a giant warehouse where you dump all your data in its raw form and then use different tools to analyze it later. It's built for scalability, meaning it can grow with your needs by simply adding more computers to the system. And while our DBMS are really good at handling individual transactions quickly, Hadoop is better suited for big picture analytics, analyzing huge datasets to find trends and patterns. Okay, let's talk about some of the hurdles Hadoop faced from the get-go. While it's an amazing system for handling huge datasets, it isn't perfect. One big thing is that it doesn't really shine when dealing with small asterisk amounts of data. The whole MapReduce process can be overkill. Also, if you need quick answers, like in a real-time dashboard, Hadoop can take a while to respond. It was designed primarily for batch processing, so interactive queries aren't its forte. Setting up and maintaining a Hadoop cluster is also notoriously complex. It's not something you can just throw up and expect it to run smoothly without some serious expertise. Finally, remember that Hadoop doesn't inherently offer strong consistency. It gives you what we call eventual consistency, which might not be suitable for all types of applications. Okay, let's talk about sequence files. Think of them as a really efficient way to store big data in Hadoop. They're basically binary files, meaning they take up less space than if you save things like CSV text files. They also compress well, often using Snappy or LZO, which helps keep storage costs down and speeds up reading and writing. What's especially handy is that they support a hierarchical structure, allowing you to organize related data within the same file. Imagine logs grouped by date. Because of this hierarchical nature, they're broken into partitions so MapReduce jobs can process different parts of the data in parallel. You'll often see them used for storing intermediate results or moving data around between different Hadoop tools. Okay, let's talk about data locality in Hadoop. Basically, it's all about keeping your computations close to the data they need. Think of it like this: moving massive amounts of data across a network is slow. Hadoop tries really hard to schedule tasks on the same machines where the data actually lives. This way, you avoid constantly sending information back and forth, which dramatically speeds things up. HDFS keeps track of exactly where each piece of data is stored, so Hadoop can make smart decisions about where to run your jobs. Okay, so let's talk about blocks and splits. They're both important parts of how Hadoop stores and processes data. A block is like the smallest piece of data in HDFS. It's always 64 MB large and gets replicated for safety across different machines. Now, a split is essentially how Hadoop divides a file into pieces that can be processed by multiple nodes. Think of it as breaking down a big task into smaller ones for different teams to handle. The more splits you have, the more work each node has to do, so managing them effectively is key to a fast and efficient Hadoop job. Okay, let's talk about custom input formats in MapReduce. Normally, Hadoop reads files using a standard format, but sometimes you need something tailored for your data. Think of it like this: if you're dealing with JSON or XML, the default way Hadoop reads text might not be efficient or even correct. A custom input format lets you tell Hadoop exactly how to read your specific data, whether it's a different delimiter, a completely new structure, or maybe you need to do some initial processing as you read it in. Essentially, it's about giving Hadoop the instructions it needs to understand your data before it starts processing it in the map tasks. Okay, let's talk about optimizing those MapReduce jobs, because let's be honest, they can be hungry for resources. The key is to minimize data movement both during the map and reduce phases. We want to get rid of as much unnecessary work as possible. First, let's look at how we can tune the shuffle phase, which is really about moving your data around efficiently. Then we'll explore using side filtering to cut down on unnecessary data. Next up are combiners. These are like mini reducers that do a little pre-processing right in the mapper. And don't forget about input formats and reducing side outputs. Those can make a big difference too. Finally, it's super important to profile your jobs with Hadoop metrics so you know where the bottlenecks are and focus your optimization efforts there. Okay, let's talk about replication factors in Hadoop. Basically, when you store data on the Hadoop cluster, it's copied multiple times to ensure that if one machine goes down, the data is still available. The default number of copies is 3. This means for every file, there are 3 identical versions spread across different machines. This provides really good protection against failures. While higher replication offers more reliability and fault tolerance, it also takes up more space on your storage drives and increases the amount of network traffic when you're writing new data. You can adjust the number of copies using a command like HDFS admin set replication, whereas the desired number of replicas. Okay, let's talk about how Hadoop can actually run. The simplest way is called standalone mode. It's really basic, good for getting started and testing things out. But when you need to scale up and handle more data, you'll want to use cluster manager mode. This is the most common approach today, and it uses something called Yarn to manage all the resources across your cluster. Think of Yarn as a traffic controller, making sure everything gets what it needs. Yarn has two main parts: a resource manager that decides where things go, and node managers that run on each individual node in the cluster. Historically, Hadoop used a different mode called MapReduce, but Yarn is now the recommended way to go for better performance and flexibility. Okay, let's talk about pseudo-distributed mode in Hadoop. Basically, it's a clever trick you use during development to mimic the look of a bigger cluster on just one computer. It's really handy for getting your code working and testing things out quickly without needing all the resources of a full, production-sized Hadoop setup. You'll need to tweak some configuration files, mainly core site XML and HDFS site XML, assigning each fake node a unique hostname and node ID. It's perfect for speeding up development and debugging, but remember, it's not something you'd want to use in a live environment. Okay, let's talk about fully distributed mode in Hadoop. Think of it like this: initially, Hadoop was often set up with just one master node managing everything. That's called pseudo-distributed. But for real-world clusters, you need more resilience. Fully distributed mode means having multiple master nodes, or name nodes. This is super important because if one name node goes down, another automatically takes over, so your data isn't lost and the system keeps running smoothly. It's all about making sure things don't break and keeping everything available. You want to understand this difference when you're interviewing. Okay, let's talk about local mode in Hadoop. It's a super handy tool when you're developing or just trying to figure things out with Hadoop. Basically, it lets you run all the key parts of your cluster like the name node, data nodes, resource manager, and node managers on a single computer. So instead of needing a whole bunch of machines running together, everything happens within one process. It's perfect for testing code, debugging problems, and really getting a feel for how Hadoop works at its core. Just remember that because it's all happening locally, it's not something you'd use in a real production setting. Okay, so let's talk about failover controllers and Hadoop. Think of them as the cluster's emergency responders. They constantly check on all the important pieces like our name nodes and data nodes to make sure everything is running smoothly. If a node goes down unexpectedly, the FC springs into action automatically. It quickly steps in, promoting a backup node to take over, so your Hadoop cluster keeps humming along without significant interruptions. This makes the whole system much more reliable and reduces the need for manual intervention. Let's talk about Hadoop federation. Basically, it's a way to combine the power of multiple Hadoop clusters into one big system. Imagine you have several smaller data warehouses. Federation lets you merge them together. Why do we do this? It massively boosts your processing capacity and adds a lot of resilience. If one cluster goes down, the others keep going. Plus, it allows you to distribute data and processing closer to where it's needed, reducing delays. The name node acts as the brain of the operation, smartly routing tasks across all the clusters involved. Now let's move on to some common questions you might encounter in a Hadoop interview. Okay, let's talk about the evolution of Hadoop. Hadoop 2.x was a powerhouse built around MapReduce. It's still used widely, but it could be slow for certain tasks. The big difference with Hadoop 3.x is that they completely revamped how data is processed. They introduced TERS, which is much faster than MapReduce, especially for interactive queries and complex analytics. Plus, Hadoop 3.x really leaned into the idea of a data lakehouse, integrating features like Apache Iceberg to bring transactional capabilities to your data lakes, making them more reliable and easier to work with. Okay, let's talk about what's new and improved in Hadoop 3.0. Essentially, this version really focused on making things a lot easier to manage and use. Jan, the resource manager for Hadoop, got a big upgrade with better scheduling and more efficient usage of your cluster's resources. HDFS, which is how Hadoop stores data, saw improvements too, particularly in its nano design, which makes it much more reliable. Hive, another popular Hadoop component for querying data, also received significant performance boosts. And because everyone wants to work with Spark now, Hadoop 3.0 provides a really smooth integration between the two technologies. Finally, Ambario Clusters Management Tool got fully automated high availability, so you don't have to worry as much about keeping things running smoothly. Okay, let's talk about erasure coding. It's a really important piece of the Hadoop puzzle, especially in version 3x. Basically, instead of just making copies of your data like you might with a traditional hard drive system, erasure coding uses clever math to create redundancy. It's based on Reed-Solomon codes, which allow us to rebuild lost pieces of information. It creates parity blocks alongside the actual data blocks, and by distributing these across different nodes in the cluster, it becomes incredibly resilient to failures. You can lose a certain number of nodes without losing any data. This is much more efficient than simple replication, meaning you get better storage space for your fault tolerance, which makes Hadoop clusters much more scalable. Okay, let's talk about the HDFS balancer. It's essentially a smart system that keeps your Hadoop cluster running smoothly and efficiently. Imagine you have a bunch of computers' data nodes storing data together without a balancer. Some might get overloaded while others sit idle. The balancer constantly monitors how much space each computer has and moves data around to make sure everything is balanced. This prevents slowdowns, ensures reliability, and helps your entire Hadoop system perform at its best. Okay, let's talk about disk balancing in Hadoop. Essentially, it's all about making sure your data isn't stuck on just one or two machines in your cluster. The name node keeps track of where each piece of a file is stored, and then uses that information to distribute the blocks across all the data nodes evenly. This prevents any single machine from getting overwhelmed, which would slow everything down. It also means you're benefiting from redundancy. If one data node goes down, your data is still available on other nodes. It's a really important part of how HDFS works to make it both powerful and reliable. Okay, so one of the most fundamental things to understand about Hadoop is how it handles massive amounts of data. It doesn't try to do everything on a single powerful computer. That's key. Instead, Hadoop breaks down those huge datasets into smaller pieces. Think of them like puzzle pieces. Then, it distributes these pieces across many computers in the cluster, and each computer processes its own piece independently. This is called map. Once all the pieces are processed, they get shuffled and sorted based on a key, so related information ends up together. Finally, another stage, called reduce, combines this sorted data to give you the final result. It's like a huge team effort. Each computer handles its part in parallel, making the whole process much faster than if one machine had to do everything itself. Pretty clever, right? Okay, let's talk about serialization in Hadoop. Think of it like packaging your data so it can travel safely and efficiently across different parts of the system. Basically, it's how we turn complex data into a stream of bytes that HDFS and MapReduce can handle. There are a few popular methods like Avro and Protobuf, each with their own strengths. Java serialization is simpler but has some potential drawbacks if you're dealing with data from outside your control. It's really key to understanding how Hadoop effectively manages all the different kinds of information. Let's talk about Avro in the context of Hadoop. Basically, Avro is a super smart way to save and transport data within your Hadoop cluster. Think of it like having a detailed instruction manual for each piece of data. That's the schema. It keeps things consistent and allows you to easily update those instructions as your needs change. Because it's in binary format, it's much smaller and faster than other formats like JSON or XML, which is great for big data sets. And perhaps most importantly, Avro makes it easy to evolve your data schemas over time without causing problems down the line. Okay, so let's dive into Parquet. Think of it as a super efficient way to store data within the Hadoop world. Instead of storing your data row by row like in a traditional spreadsheet, Parquet stores it column by column. This is a huge deal for performance because when you're running queries, you often only need specific columns. Parquet then only reads those columns from disk, skipping everything else. It also compresses the data and has built-in mechanisms to handle changes to how your data is structured over time, which is incredibly helpful as your data evolves. Basically, it's all about minimizing the amount of reading needed, making queries much faster. Okay, let's talk about ORC-optimized row columnar. It's a really important storage format for Hadoop and other big data systems. Think of it as a super efficient way to store your data. Instead of storing rows like in CSV files, ORC stores the columns together. This makes reading only the specific columns you need during a query much faster. Thus, because of clever compression techniques, it saves you *ton* of storage space. It's designed to evolve as your data schema changes, making it super flexible. Parquet is another columnar format, and both are good options, but ORC tends to have the edge when it comes to compression. Okay, let's talk about columnar file formats, a really important concept for understanding how Hadoop works. Instead of storing data row by row like in a regular database, columnar formats organize it by columns. It's like sorting your spreadsheet by category: sales figures, customer names, product ID, whatever. This is incredibly helpful because big data systems, especially Hadoop, are really good at doing analytics. When you need to analyze just one column, say, all the sales for a particular product, they only have to read that specific block of data from storage, which saves *ton* of time and resources compared to reading every row. Okay, let's talk about how we keep an eye on our Hadoop cluster. Monitoring is absolutely essential. First off, there's the Hadoop metrics system, which gathers data from all sorts of parts of the system. Then we have Ganglia, a really handy tool that pulls information together from across the entire cluster. And for visualization and alerting, you might use tools like Nodjos or Zabbix. Basically, they help you spot problems before they become major headaches. Things to keep an eye on include CPU usage, memory, disk space, network activity, and how long MapReduce tasks are taking. Setting up alerts based on thresholds for these metrics is key. It's about proactively identifying potential issues. Okay, let's dive into job history servers. They're super useful when you're dealing with Hadoop jobs. Imagine every single MapReduce task that runs on your cluster gets meticulously logged. That's essentially what a job history server does. It keeps track of everything: the unique ID for each job, its current status, is it running, did it fail, and a detailed timeline of when each stage like the MapReduce task started and finished. It also records how much data was involved at each point. Why is this important? Well, it's invaluable for debugging problems, monitoring your cluster's overall health, and even ensuring you have an audit trail if needed. Okay, let's talk about how Hadoop works with the cloud. Think of Hadoop as a really powerful engine for processing huge amounts of information, but it needs somewhere to start its journey. That's where cloud storage like S3 or Google Cloud Storage comes in. Instead of storing everything locally on your own servers, you upload your data to these services. Then Hadoop jobs can directly pull the data they need from the cloud, bypassing huge network transfers. It's a win-win. It reduces bandwidth demands and makes things way more scalable. Okay, let's talk about how Hadoop handles growing amounts of data. Essentially, we have two main ways to scale: vertical and horizontal scaling. Vertical scaling is like upgrading your computer with a faster processor or more RAM. It's simple, but you eventually hit a ceiling on what you can add to one machine. Horizontal scaling, on the other hand, means adding more machines to the cluster. Hadoop is specifically built for this. It distributes the data and processing across many nodes, letting you handle massive amounts of information with ease and added reliability. It's all about building a robust and scalable system. Okay, let's talk about how Hive handles changing table structures. It's something we need to be really good at managing. Because data is constantly evolving, you'll often need to add new columns, drop old ones, or rename existing ones. The key here is that Hive doesn't automatically update tables when you make these changes like some other databases do. Instead, there are a few clever techniques you can use. You can simply add or remove columns, change column names, and even create views to present different schemas without directly modifying the underlying data. Thus, Hive's Metastore keeps track of all these changes, which is really helpful for debugging and understanding how your tables have evolved over time. And remember, always test the schema changes on a staging environment first. It's essential. Okay, so when we talk about big data processing with Hadoop, it's not just a simple throw everything in situation. There are some serious hurdles to overcome. Primarily, scalability is huge. You're dealing with datasets that are way beyond what traditional systems can handle. Then you have the variety of data itself. It's not always neatly organized like a database table. You might be pulling in JSON files, XML documents, or even images and videos. Handling all those different formats efficiently is key. Of course, the volume of the data itself is immense, making storage and processing incredibly complex. And don't forget fault tolerance, because you have so many machines working together. Things will go wrong, and Hadoop needs to be able to recover gracefully. Finally, managing the cost and resources involved in running a large Hadoop cluster can add up quickly. Thank you for watching.